Hey guys, welcome back to another RESK Maths tutorial, and in this video I'm going to be solving a sort of challenge question or just a fun question, and it's basically to find all the integer solutions to a to the b equals b to the a, and I should probably add another condition that a is not equal to b, just because otherwise it becomes too easy. But anyways, the point of this is to show you something pretty interesting about the solutions and more that the number of solutions, so we'll get to that. But yeah, let's just start solving this. So we have a to the b equals b to the a, and immediately you're going to see two variables and only one equation. So you might be thinking, how are we going to solve this? Well, we should probably start by we should either try and get b in terms of a in terms of b. We could do that, or what we could do is we could try and get a on one side and b on the other side. So try to separate them out so they're not interdependent on each other. So that's the route I'm going to take. And first thing, since we see exponents, we're going to try and take logs. So I'm just going to use ln, and let's take ln of both sides. Then using our log laws, we can take the powers down into the multiplications, just like this. And then what you can do is we can simply rearrange to get ln a over a equals ln b over b. Ln is natural log. Okay, so we've rearranged the equation from this form into this form. And now we have a and b as separate things. Separate sides. And you can see they're also both in the same form, which is convenient because now you're going to see what I can do is let's define a function f of x is equal to ln x over x. And you might be able to see where I'm going with this. What we're trying to do essentially is this equation now simplifies into, let me just highlight this since it's quite important. Essentially what we're trying to do is we're trying to find a value of f of a which is equal to f of b, such that a is not equal to b, just like that. And graphically on a graph, what that would look like is if this was f of x, what we're looking for is a like single y value or output of f of x, which is the same for two different x values, x1, x2, and a constant y. We're looking for two different x values, a and b, which give the same output, and a and b are different. So to do that, we probably want to sketch f of x. So let's try and do that. Sketch f of x is equal to ln x over x. So obviously with sketches, you want to find where the turning points are. So let's work out the derivative of this using the quotient rule. So v du, which is just going to be x times 1 over x, minus u dv, which is just 1 times ln x, all over v squared, like so. And we want to find the stationary points. So this is where f dash of x is equal to 0. And putting this equal to 0, I'm just going to do some quicks. Going to simplify this a little bit, and we're going to times both sides by x squared just to get rid of that. So we get 1 minus ln x equals 0, or ln x equals 1, so x must be equal to e. So this is the coordinates of our stationary points. We can determine what the nature of a stationary point is going to be, either by using the second derivative, or we could just simply look at values either side, or we don't even need to do that because if we just look at how this function changes, so let's look at f of 0. Actually, let me just do something. So let's go back here. F of x is ln x over x. As x approaches 0, ln x is going to approach minus infinity, and x is just going to approach 0, right? So this is a minus infinity over 0 situation, specifically 0 plus. So this means f of x is also going to approach negative infinity, and as x approaches infinity, Well, this is going to be ln x over x, which both approach infinity as well. However, x actually approaches infinity at a faster rate than ln x, because ln x is known to be a really slowly increasing function. You can see by the graph, this is going to be x, this can be ln x, so x is definitely going to be greater than ln x, even though they're both technically infinity. Let me just write, however, ln x increases much slower than x. Therefore, as x approaches infinity, f of x is going to approach 0, because we're going to get something like a much smaller infinity over a much larger infinity. So f of x approaches 0. So now we have this data. We know that there's a stationary point at x equals e. At x equals e. And y coordinate of this is just going to be linear over e, which is just going to be 1 over e. We know that as x goes to 0 plus or 0 from the right side, f of x goes to minus infinity. And we know as x approaches infinity, f of x approaches 0. The last thing we might want to work out is any roots. So let's just solve f of x equals to 0. And pretty easily, you should be able to see that this is going to be true when x equals e to 0, which is 1. So we have root, there's a singular root at 1, 0. And this is basically all the information we need to sketch the graph of this. So I'm not going to care about the negative axes, just because we don't care about negative values for a or b. So we're only looking at the positive quadrant for now. And we have a root at 1, 0. Let's put in the asymptote at y equals 0. And there's also an asymptote at x equals 0. And let's just take this graph up. Let me make it look a bit better, like so. And, okay. This graph is not to scale, but hopefully you can see that this stationary point must be a maximum, because this curve has to come down eventually. If it went to infinity, then it might be a minimum, but it would have to be something like that, right? And there's definitely no other stationary points, so there's no way for this to come back down without it either having 2 more stationary points or 0 stationary points. So, yeah, hopefully it makes sense why this is a maximum. And yeah, that's about it. So this is what our curve looks like. And let's remind ourselves of the original goal. We're trying to find a value f of a, which is the same as f of b, and a is not equal to b. So you can see that this curve actually comes down in itself, and we're only interested in this region here. This is going to be x equals e, which is approximately 2.7. And you can see all values in here, they're going to have 2 roots if we draw a y line. But anything past this is going to have 0 roots, and anything underneath this is going to have 1 root from the minus sign. So we're interested in all the values within this line, because these are the sort of y lines which are going to give us multiple roots. So therefore we have multiple possibilities for a and b. And within these, we're looking for integer values of x. So the only integer value of x within this is actually 2, somewhere over here, because 1 is already a root. So if we try and draw a line there, we're never going to get a solution, because this has an asymptote at x equals 0. And there's no, if we have 3, right, there's nothing past that. There's nothing here. It's not going to work. So the only possible value we can check is at x equals 2, like so. And if we draw this line in, you'll see this clearly has another point of intersection. So let's just call this value x. We'll just say we want to find this. So this point is going to be 2 ln 2 over 2, right? And we're trying to find this x and hoping that it's an integer. So we can set a to be 2. We've already got that. And now we're trying to solve for f of b is equal to ln 2 over 2, where b is not equal to 2. So here's the full equation. Ln b over b equals ln 2 over 2, with b not being equal to 2. Now, it would be really easy to just put b as 2, but obviously we can't do that because then b would just be equal to a, so we wouldn't have a valid solution. But look what happens to this ln term, right? So this is ln 2 over 2. If we multiply top and bottom by 2, then we get 2 ln 2 over 4. I'm going to write it as 2 times 2 just to make something clear. And using ln laws, we can actually move this outer 2 into the power over here, get 2 times 2. And what does this leave us? We get ln 4 over 4. So here's another solution for b. b is equal to 4. Now the reason we're able to do this, and the reason why there's no other solutions, is because 2 is the only number where if you raise 2 to the 2, that's the same as multiplying by 2. There's actually no other number which does this, at least. I don't think there is. So there's our solutions. We've got f of 2 equals f of 4. Now remember what that means. A equals 2, b equals 4. And remember what the original equation was. Therefore, 2 to the 4 equals 4 to the 2, which we probably knew, but now we've managed to prove that this is the only solution. This is the only solution, and the reason is because these values in here, these are possible values for a. Everything past this turning point is possible values for b, and within this part, there's only an integer. X equals 2 is the only possible integer because there aren't any other integers within this thing greater than 1 and less than 2.7. So yeah, that's what I wanted to show you, is the fact that this is the only kind of equation where a to the b equals b to the a and they're both integers. That's the only solution, and hence 2 to the 4 equals 4 to 2 is the only answer. Anyways, thanks for watching. That was just an interesting way of proving that this is the only solution to a to the b equals b to the a. I actually took inspiration from a step question. I'll probably be posting more of those in the future. But yeah, thanks for watching, and I'll see you guys in a future tutorial. Bye!